Yes. Welcome. So we aren't quite finished with the conjugate gradient method. We are so far we've only looked at the linear conjugate gradient method, and then we ended up with this algorithm or method to actually perform it. So over here we have the starting vectors. So we start with R0 equals b minus a. We are again trying to solve the system a x equals b, like so. And this is repeat from last lecture. So this should be known. But there was one thing I didn't have the time to discuss, and that was the nonlinear conjugate gradients. Nonlinear CG. So now we will try to solve the general problem to find the minimum x that solves this function f of x, which can be linear, nonlinear, whatever you want. So changes are that we can't use the recursive formula for the residuals. It's also more complicated to compute the step length alpha, and there are several choices for this beta constant. Over here, we were talking about two of them. So what we can do, first, how to guess this alpha? Well, you could just guess it. That's often been done. So, but we can use any algorithm that solves the problem f by plus alpha ti your t here transposed I. So if we try to minimize this for alpha, then we have found the optimal step length. Sorry, yeah, sick today. So a naive approach here is basically just to guess a step length, and if that doesn't work out, you try half of this step length, and if that doesn't work, you try half of this again. It's not perfect, but it works. That's actually how we've implemented it in our code when we do full waveform inversion. We are using the conjugate gradient method, and the best solution to actually find this alpha that isn't very computationally expensive is to just guess a value and try to evaluate the function and see if this is better than the previous step. And if you can't find any better, then that's the best we can do. So basically, I'm sorry, just guess. Or you could try to solve, but then you need to find the Hessian. So I E, so double of I, the I. That's also an estimate. You see, instead of using the A here, we are using the second derivative of our function. But then we need to be able to actually calculate this in a reasonable manner. It's also a different way of picking the alpha. So if the new function evaluation, I'm going to call this here f new. So f new less than f old. Well, then we'll pick the good alpha. alpha. If not, we try a different alpha, usually a smaller. As long as you try to do this in a well, if you have some logic behind your process, then it should be okay. Just not, well, throw a die and some dice and see if, yeah, this is going to be a new alpha. If that doesn't work, you just like roll some new dice and see if this is your new alpha. Do it in a controlled manner. So that's for alpha, and then beta. You have many choices for them, but I will list two of them. That is the Fletcher-Reeves. Beta. So we have the Fletcher-Reeves. That is, and you will try these upcoming exercise. Oh, this is actually the same. So, T and RI RI. So this is the same. And so that, yeah, this is just the same as we did with our old one. And if that doesn't pan out, we can try the Pollack-Rivière. Rivière. Or, yes? Yeah, it's supposed to be RI. Yes. Yeah? No, that T was supposed to be there. This one is a slight difference. Because in nonlinear, you can kind of run out of directions. So this will be. So this is the same problem you will run into as for the Paulus method, only with gradients instead. So you're basically empty of directions. So it is Pollack-Rivière. It tends to converge faster, most often, but it might also cycle infinitely, meaning that you've your minimum point is here, and you will just cycle around it all the time, so you will never find the optimal here. And then you can also have hybrid methods where you see if you're cycling, you can switch to this Fletcher-Reeves. But also, if you start cycling, a good way to eliminate that is that if you pick your beta to be the maximum, this beta I, or yes, PR, and 0. So that means this can actually be a negative number. If it's a negative number, you just say it's 0, and that basically means that you're resetting all your search directions, which does make sense if you are in a nonlinear function. So, to summarize. Okay, so yeah, if you pick 0, you restart conjugate gradient. First, you have to find alpha that minimizes. It doesn't have to be perfect, just better. Xi alpha di. I mean, mathematically, you want to find the alpha that actually minimizes this. But that, I mean, finding the exact minima, yes, that would take a while. Because you would just want to minimize this. So that means a lot of function evaluations. And here could actually use the golden search method. So just one-dimensional problem. So if you have an interval for your alpha, it's supposed to be between, well, 0 and 1, for instance. Then you start with these outermost points, and you can go in, try. Or you could just shoot and see where you end up. And then you have to update I alpha I the I there as well. Take the rest or residual. Delta f xi plus 1. Yep. And then compute the I. Or beta I, sorry. And you have your new direction. I equals Ri plus beta I plus 1. Any questions about the conjugate gradient method? Not, we'll start on interpolation, which is how can we approximate functions? Well, approximate them with polynomials up to an arbitrary degree of precision. Yeah, I'm just going to. So I assume most of you have had something to do with interpolation before. We'll try to start with an example, which I've picked from the book, unfortunately. Or we can do a better one. So, numerical relation. Okay, so say that you have the bus ticket prices here. This is from the old prices. But if you look at ATB's bus prices for period cards, it's for day. So for days, you have 7 days, 30 days, 20 days, 150. And then you can actually pick how many days you want your period to last. But what do you want to pay then? So they've listed these prices. Cost 7 days, that's 135. Again, these are all prices. 760, 90 days. I think these are adult prices, not student, though. Still expensive. 3,115. This is going to look somewhat like this. See? Cost. And days. So 7 days down here. 30 days, that's purple, maybe. There, 90 days again. Here. So you could just do a linear interpolation here. If I remember correctly, that doesn't quite work. But we can actually use this to estimate how much, if I only want 60 days, so say it's 60 days until I leave Trondheim, never coming back, how much should I pay for my period tickets? Well, we can use this data and then we can interpolate and we can figure out somewhere around here. Find a price. See, and that's going to be 1,005 or 60. But how do I get this number? That is what we're talking about. And this is a pretty simple interpolation. But it's useful for everyday not transactions, but problems. Also, MATLAB has inbuilt numerical interpolation, especially in the in the plotting routine. You can actually check your answers. So, interpolation is done with the help of polynomials, most often. Meaning that we want a polynomial En of x on the form an. So this is called the canonical form of a polynomial an times x to the power n plus some coefficient an minus 1. 1 all the way to a1 x all to the power of 1 plus some constant 0 or x to the power of 0, which is 1. And of course, there's a good name for theorem why this works, which is Weierstrass approximation theorem. Again, the canonical form. Or canonical just means the normal form or how it's most well written. canonical universe. Good. Oh. Anyway, theorem. Fire. Stress. Theorem. That is. Almost shock. Assume that that f is a continuous function. Find and continuous on a interval AB. B, and then for any and again with this epsilon bigger than 0, there exists a polynomial x such that the difference function f x p of x less small number for all numbers inside this, like so. This basically just tells us that yes, we can do interpolation. And how can we do interpolation or approximation? Well, you have used Taylor polynomials. We have used Taylor polynomials. They don't always work, but let's see how they pan out. Taylor polynomials work pretty great close to where you expand them from, but other than that, not really that great in general cases. Taylor polynomials. So we are going to assume that f is continuously differentiable. I assume that f is in continuous space n+1 differentiable on the interval AB. So the C, that's not a complex plane, it's just continuous functions that are n+1 times differentiable, at least, in interval from A to B. Triggers. and that we have a number x0 inside this interval. Fixed value. So this x0 is just arbitrary, we just picked it, just something, a number. Then we have that the function f of x is equal to e of n, polynomial, plus some kind of error term, n. En is call it a polynomial that approximates f of x. F of f x is approximately equal to n of x is x is, as you've seen before, the finite sum from k equals 0 to big N f k. So this k is how many times been differentiated. The point 0 over k factorial, or fakultet in Norwegian, times minus power of k. And error term with the error en. Well, that's going to be the next one. F n plus 1 of some number psi n plus 1 factorial x minus 0 over of n 1. Can you see down here? Some chi of xi, maybe it's xi x in my interval b. Then this one is just going to be a number. Okay, an example with this. We see Taylor polynomials doesn't work. We try to approximate e to the power of x on the function. Oh. Example. We are given the function f of x ux, and the point 0, we just 0. Okay, and then we can figure out the Taylor polynomials. This. According to this Weierstrass approximation theorem, we should be able to find a polynomial that is as accurate as we want, but then we need to go very high in the polynomial degree. So let's see. E0 x. Oh, that's just going to be 1. First degree is 1 plus x. And if you want, you can calculate these yourselves, but I suppose you've done it plenty of times before. 1 plus a half x squared. And then I'll do one more. P3 of x. 1 plus a half plus 6th x to the power of 3. So the thing is to see here is that this Taylor polynomial, it only uses information around the point x equals 0, meaning that it's going to be accurate around 0, but other than that, it's going to diverge. So it's less accurate away from 0. So we try to graph this. See that like this, the power of x, whereas, well, the first one, that's just 1, okay, or so the first one, 0, E1, straight line, oops, like this, P1, P2, well, add some curvature, 2 and P3 might add even more curvature. For the higher and higher degrees, they will be more and more accurate. You skeptical? Okay. Okay, so in this case, yes, there should be a plus x inside here, of course. Thank you. Plus x, of course, my bad. And actually notes has. Okay, so here it kind of works. You can just keep adding higher and higher degrees of polynomials, and you will approximate e to the power of x better and better. But in some cases, it just breaks down. So a different example is if you try to approximate x 1 over x around, well, it's kind of silly to approximate this around 0, so it's going to approximate it around 1. Okay, the derivative of x going to be 1 over x squared 2 times differentiated as sine 3 and x 1 a times polynomial x to the power of minus a minus 1. Okay, so we want to use this formula to approximate f of x 3. So we want to approximate third using polynomials. So this is just 0.333 recurring. What happens if we try to do this with polynomials? Well, I'm going to have the degrees here, and then I will have the polynomial 3. Okay, when we have a polynomial of degree 0, it's just going to be 1. Polynomial of degree 1, then we have minus 1. Shouldn't work. 2, we have 3. If you have a polynomial of power 3, we get minus 5. If you have a polynomial degree 4, we evaluate this polynomial, we get 11, and so on and so forth. It's just going to be worse and worse and worse. So Taylor polynomials doesn't work in this case. So we need something better. We need a better way of constructing polynomials such that they can actually fit more functions. It's supposed to be a table. So how do we construct better polynomials? Well, we're going to go through 2 ways of doing it, or through algorithms of constructing polynomials that will fit arbitrary functions. The first one is going to be Lagrange polynomials, and the second one is going to be Newton polynomials. Each of them has their own advantages in how to compute them, but you have to you should know that you get the same polynomial as long as you have the same numbers. You're trying to the same points you are approximating around. You will get the same polynomial if you pick the Newton algorithm or your Lagrange algorithm. But first, the Lagrange. Just brief introduction to them, and then we take a break. Yeah. Let's see. So we want idea is that we want our polynomial to pass through certain points. Given points. So say that we want a polynomial of degree 1 that passes through 2 points in the plane, say point x1, call this 0, f of 0. We have point x1, f of x1. Then we want, in this case, to construct just a line. We don't care if maybe f of x looks like, oops, that function might look like this. Because here we've only done, we've only been using 2 points. If you use more and more points, then you can approximate this function f of x better and better. Less and less error. So we're constructing a line that should be known, but state or goals. So we want a function, so we know that 0 equals y0 and f of 1 equals y1. So we want to construct, in order to actually have a function with the same properties, such that L for Lagrange, L 0, so you get I1, L of x1 should also be y1. So we can define L 0, so the first term, x be x minus 1, 0 minus 1, L1, x minus x 0, and x1 minus 0. So if we then construct our polynomial, I'll call them L, but that. So that's our final polynomial, should have these properties. We now just construct this as the sum of these, a weighted sum, 0 of x, f of 0, plus L1 times of x times x1. We see that we have these properties. Thus, when I insert x equals x1 here, L0 becomes 0. And if I insert x0 into this, it's 1. And different there. So see that 0 of x0, 1, 0 of x1, 0, and L1 of x0, 0, L1, 1, 1. And then we'll try to generalize this a bit more.